Very well. We are about to see what we can do with acyl chlorides through and through. And since this type of molecule is at the top of the chain in terms of reactivity, what that will mean is that we're going to be able to produce the vast majority of the variants of the derivatives of carboxylic acids straight out from acyl chlorides. All right, so let's start with the first one, which is transformation of the acyl chloride back to carboxylic acid. Um, you might think that this is a little bit silly, especially being the case that you do make acyl chlorides only from carboxylic acids to begin with. So, it may seem kind of weird that you might want to go back to carboxylic acid from this. Nonetheless, if you do expose your acyl chloride to water, either on purpose or accidentally, what will happen is that the water will attack the carbonyl carbon center of that acyl chloride. It will push away the electrons back to oxygen, and it will create this intermediate right here where you have an oxo anion, and then you have your hydronium cation on one end. So technically still a neutral molecule, but you are producing charges within the same molecule. So what will happen then is that because you do have the chloro leaving group, which is as good a leaving group as it's going to get, the oxo brings back down a pair of electrons to create a double bond, and in the process kicks away the chloride, thus yielding a protonated carboxylic acid. And of course, the last part right here is that you deprotonate that protonated carboxylic acid, right, using the chloride, kicking the electrons back to oxygen, and that's shielding your carboxylic acid. So when you handle acyl chlorides, the key idea right here is that, you got to do this under sealed flasks. You use syringes, you use inert solvents, solvents that are free of water specifically, because if you just do this in open air, you might be able to do a couple of reactions with that, but you will be killing a good chunk of your reagent just by exposing it to the atmosphere. And it's not necessarily like a very crazy reaction, although you could be producing some amount of HCl in the process. So if you're doing this outside the fume hood, which will be a very bad idea, you could be inhaling a bunch of HCl gas. Okay, now just like you could do this with water, you could also do it with a stronger base. And basically, yes, you could treat your acyl chloride with hydroxide. You could use sodium hydroxide specifically, and here you could do it technically under aqueous conditions, or you could just like add the sodium hydroxide pellet to it. This will be a pretty strong reaction through and through. So you kind of have to watch out for exothermic, runaway reactions, if you will. But the hydroxide will basically do the same thing that water did. It will attack the carbonyl carbon. It will kick away the electrons of the CO double bond, forming the following tetrahedral intermediate over here. And then the electrons of that oxo group, or oxide group rather, will come back down to reform the double bond while kicking away the chlorides. And since you have sodium around, the moment the chloride comes off, you eliminate sodium chloride ultimately. Now, the carboxylic acid that's initially formed is technically acidic, very acidic compared to hydroxide. So what's going to happen is that you will initially deprotonate the carboxylic acid, form the carboxylate, and then if it is in fact the case that you do want the carboxylic acid, you will have to protonate it again during workup. But other than that, this is basically how the whole mechanism goes. All right, now starting from the acyl chloride, we can go to the anhydride, and we showed this already a little bit earlier in the discussion. But just to remind you about it, yes, you start with the acyl chloride, but the way you do this very efficiently is to do it with the sodium carboxylate salt that you're trying to fuse together. The carboxylate attacks the carbonyl, the double bond is broken up, you form the following tetrahedral intermediate, and then the oxide set of electrons comes back down and the chloride takes off, right? And so that leaves you ultimately with your anhydride, and in the process you've also crashed out some sodium chloride salt. So that's the most efficient way to do it. Now, tributol, you could even do this with just regular carboxylic acid, but in my opinion, this is the best way to do it. So I would stick with this method particularly. All right, now esters. The way you make esters is pretty much the same as the way you make carboxylic acids. You simply expose your alcohol to the acyl chloride. So instead of being water, now it's alcohol, but the idea is still the same as before, namely that your alcohol attacks the carbonyl carbon center. You kick away the electrons back to oxygen. You form this tetrahedral intermediate, and the oxo allows its electrons to come back down to reform the double bond while kicking away the chloride, right? So you could probably see that all this set of mechanisms follow the same trajectory over and over, right? Because we're still dealing with the same initial substrate. It's just the nucleophile that's changing from reaction to reaction. All right, but once you kick away the chloride, you still have the protonated ester. And the last thing that happens is that you have your chloride attacking your proton and bringing the electrons back to your oxygen, thus shielding the final ester. So this is a pretty efficient way to get your actual esters. But truth be told, you could also do this with the alkoxides. Now, in my opinion, probably it's best if you just do it with the alcohol because it's readily available, convenient. You don't have to deal with strong bases that could get protonated by water necessarily. So this is less useful in my opinion, but it's nonetheless very efficient once you get it under the right conditions. So the alkoxide, in this case methoxide, is simply going to do the same thing. Attack the carbonyl carbon, kick away the electrons back to oxygen, form the tetrahedral intermediate, and then we'll have the elimination step where the electrons come back from the oxide to reform the double bond and kick away the chloride. And right then and there, you form your ester, right? And of course, you have also kicked away sodium chloride in the process. So it's a simple method. But like I said, sometimes having the alkoxide as opposed to the alcohol, has some difficulties associated with it. It's not like super difficult to handle it, but you have to think about potentially killing the alkoxide in the process. All right, almost there. We can get from the acyl chloride to the amide, and unlike the carboxylic acid reaction, this one is actually very efficient. And here you don't have to deal with the pHs or anything like that because you're not actually doing this in aqueous solutions at all. In fact, you don't even need a catalyst. You just have to bring the neutral amine in direct contact with your acyl chloride. And this being a good base is also a pretty decent nucleophile. So it attacks your carbon center. You break the carbon oxygen double bond, creating the tetrahedral intermediate shown here. And then what happens is that the oxide comes back down to reform the double bond, kicking away the chloride, right? And then now you have your protonated amide, which means that the last step is simply the protonation, right? Now, in the previous examples, we've been using Cl minus because for the most part, that was like the better base available. But this time around, you're doing this in the presence of amine, which is a much better base than chloride will ever hope to be. So I personally would say, yeah, just stick to using the amine base for the deprotonation. And yes, you attack the proton, the electrons go back to the nitrogen, you end up generating your amide, and you also end up producing one equivalent of your alkyl ammonium chloride salt, which you have to get rid of, doing workup. Usually those things will solubilize in water, so you just do an aqueous workup and get rid of it that way. All right, so that is basically all the mechanisms that show you what you can do with the acyl chloride. And it's a pretty versatile reagent to produce all the other types of carbonyl. So in a synthesis strategy, I would recommend you to go to that acyl chloride and then go from there to the other functional groups. But that being said, be aware of the mechanisms, because it's not out of the question for me to ask you to show how you make an ester from a carboxylic acid as opposed to an acyl chloride, and you're going to be able to do those kind of things. Okay, so next I'll show you the chemistry of anhydrides and the conversion to other derivatives, but we're going to save that for the next video. So I'll see you there. Bye bye.